Start recording. Okay, so we have last day when last we left, we had been looking at electrolytes, which have mobile ions in solution. Okay, now non-electrolytes do not have mobile ions because when a covalently bonded substance dissolves, instead of having things dissociate, instead they do what? They disperse. Okay, and you'll notice that the particles have no charge. This is page 3, actually. So they are neutral molecules, and therefore they do not conduct. All right, so covalent molecular solutes are non-electrolytes, except for acids, because we know that acids do what? Acids what do ionic compounds do? They dissociate. What do acids do? They also dissociate. Okay? And acids are molecular compounds, but they do dissociate. Go for it. Yeah, absolutely. Yeah. Oh, what happened? No, come back. Not you. My screen. Okay, so pure water, which is a covalent compound, is a non-electrolyte. Even though it does begin with an H, it does not dissociate into ions. We'll learn that I'm lying to you a little tiny bit because in grade 12, we'll learn that it does dissociate, but like only a little itty bitty bit, not really enough to conduct electricity. Yes? Okay. However, water is a polar molecule. What is a polar molecule? A polar molecule has a slightly positive end and a slightly negative end. So that's what water is. But overall, does it have a net charge? Does it have an overall charge? No. So if we look at our water and we put some electrodes in. Okay, we've got our electrode over here. And that's our negative electrode because it's got negative charges all over it. And over on the other side, we have our positive electrode. Because you can see it's got the little positives all over it. And if you remember your symbols from physics, what does long line represent? No? This is a battery, okay? And the long line is the positive terminal. And the short line is the negative terminal. What do you notice about all of the water molecules that are sitting here in between the negative electrode and the positive electrode? What do you notice about all of them?
They're facing one direction.
They're all facing the same direction. Why are they all facing the same direction? Yes? Because they have a slightly positive end and a slightly negative end. Which direction does the slightly positive end face? It faces towards the negative electrode. Okay, so the slightly positive end points towards the negative electrode. And the slightly negative end towards positive electrode. Now, there will still be random movement. The particles will still move around, but they'll kind of, instead of moving around like this, yes, they'll move around like this. You see the difference? They're not rotating, right? They can move like up and down and side to side, but they're always going to be oriented in that one direction, okay? So the water molecules still move, but they always stay pointed in that one direction. Unless you turn the electric field off, of course. If you disconnect it from the battery, then everything will just go back to normal. Is this going to conduct electricity? No. And let's prove that, shall we? I have here a conductivity apparatus. Okay? It will, you can basically see we've got a couple of wires here, okay, but they're not touching. So we're not going to have a complete circuit. So when I plug this in and turn it on, nothing is going to happen, hopefully. Okay, plugged in, turned on, and let's see if I can find my water beaker. H2O. So let's see what exciting things happen when we put this in the H2O. Ooh. Ah. Everyone with me? Ooh. Ah. Okay, super exciting. All right, so we're going to leave that for a moment. We have some videos and animations. I'm not going to show them to you today because I was unable to do it in first period and I want to get through the same amount of stuff. So I will show you those to you on Monday. Okay? So that's basically it for 8.1a. We're going to move to 8.1b, which is on page 7. So here we have a focus on dissociation. So what types of substances are we going to be focusing on here? Ionic. Okay, we could also have acids, but this particular one focuses on ionic substances. All right, and what we're going to do is we're going to take a look at these. You're going, for each of the following, we're going to write the dissociation equation. We are going to identify the ratio of particles, and we're going to draw the ions present in the correct ratio. So we have, and these first ones are just examples, so you don't have to do anything for this. Here we have some sodium nitrate, and it is solid. Okay, alternating sodium nitrate, positive, negative, positive, negative. And now we're going to throw it into water. Will it dissolve? We have sodium and nitrate. Will it dissolve? Yes, all sodium salts are soluble, all nitrate salts are soluble. So here we go. Now these ions are free to move. Okay, so we have freely moving ions. In solution. And what do we call it when we have freely moving ions in solution? That type of solution is an electrolyte. Notice that the polyatomic ions stay intact. They don't break up into N's and O's, okay? Polyatomic ions stay intact. And I think there's a little label over here that says it, so I don't need to write it down. Look at that. There they are. Okay, they don't come apart. They're held together by covalent bonds, and covalent bonds do not break in solution, right? We would have like an N and an O and an O and an O. Is that right? Is there one double bond or two double bonds? I think there's only one double bond. Nope, there's two double bonds. Is there? Yeah. Okay, that's nitrate, and it just stays intact like that. Now, when you are doing these exercises, you do not need to draw the solid because it becomes a right pain in the arse when you don't have a 1-to-1 ratio, okay? Now, just before we move on to the next one, we're going to look at our 1-to-1 ratio. When we write our dissociation, we start with NaNO3, solid, and we have one of those. The coefficient is 1. And when it dissociates, we end up with Na+, we have one of those, and we have one nitrate. Yes? So in our beaker, we need to make sure that for every one sodium we draw, we also draw one nitrate. Is good? Okay. So if the concentration of NaNO3 is 0.2 molar, then what will the concentration of, ooh, that was ugly. What will the concentration of Na plus equal? What's the ratio? 1 to 1 to 1. So if I have 0.2 molar NaNO3, what is the concentration of Na plus? 0.2 molar. Yep. And what is the concentration of NO3 minus? 0.2 molar. So stoichiometric ratios, the mole ratio works for ions in a dissociation equation, just like it does for any other sort of reaction, okay? All right, let's take a look at our next one. And you can see here the solid salt that we've drawn. What is the ratio of K's to S's? There's 2 K's for every 1 S, okay? And so when it dissociates, it will also dissociate in a 2 to 1 fashion. So when we write our dissociation equation, we have a 1 here. We have a 1 for the sulfur, but for the K, we have a 2. And you can see it becomes hard to draw them in solid form. Yeah, so I'm not going to make you do that. But what you should do is when you write it as, and when you're drawing it in solution, you should make sure that if you have 3 S's, how many K's do you need? 6. If you drew 2 S's, you would need 4 K's. Okay, so just whatever you draw, make sure you have the ratio correct. All right? Okay, now what if the concentration of K2S, if that was equal to 0.1 molar, then what would the concentration of K plus be? 0.2, because we've got that 2 coefficient in front of the K. And concentration of S would be 0.1 molar. Okay? And again, we have an electrolyte. There we go. Common errors when writing dissociation equations. So we're going to write the dissociation for MgCl2. Things that students will often miss when writing a dissociation is they'll miss the ion's charge, or they will miss writing aqueous. Okay, so make sure that you do that. Now, when we dissociate, is the other product Cl2 aqueous? Or is the other product, whoa, what happened? It jumped. Is the other product 2Cl minus aqueous? Yes.
2Cl minus?
It is 2Cl minus. Okay. Sometimes people think that it has to be Cl2 because Cl is a diatomic element. But you have to remember these elements are only diatomic when they are in their elemental state. That means not in a compound. So if we wanted to look at elemental chlorine, we would say, okay, I would start with 1 chlorine atom, and chlorine is in group 17. So if it's in 17, it has 7 valence electrons. So we got 1, 2, 3, 4, 5, 6, 7. Is that a full stable shell? No. So what chlorine does is it buddies up with a little partner, and they say, I will share an electron with you, and you will share an electron with me, and we will both be very, very happy. Yes? So here we have those electrons being shared. That is our single covalent bond. And we can rewrite that single covalent bond as a line in between the two. How many electrons does a line represent? 2. So if we want to say how many electrons does the chlorine on the left have, we have 2 in the line, 3, 4, 5, 6, 7, 8 electrons. So now that chlorine is stable. All right, our other one, we have 2 in the line, 3, 4, 5, 6, 7, 8 electrons, so that also is stable. However, we weren't given chlorine Cl2, we were given MgCl2. How does chlorine get a full shell in MgCl2? It grabs some electrons from magnesium, so they don't have to share with each other. Okay, so magnesium gives an electron and fills in that space. It gives an electron to the other chlorine and fills in that space. So here we have, this is 2Cl minus, not Cl2. So when they separate in solution, this is going to be your Cl minus ion. Okay, not a Cl2. So our dissociation equation then looks like this. MgCl2 solid gives us Mg2 plus aqueous plus 2Cl minus aqueous. There's some exercises. We're going to leave those for later. And we're just going to go through a few things here so that you can do this over the weekend. This is on page 11. How do you know if a compound is ionic? Metal or NH4? So you'll be able to go through here and you'll be able to say for each one of these compounds in number 1, whether it is ionic or molecular. Yes? Some of the molecular compounds will be acids. So then what you're going to do is you're going to go through and circle all the compounds in question 1 which are acids. Yes? This is just getting you good at recognizing compounds, getting fast at it. Okay? And then you're going to do some practice writing the dissociation equations. Now, just a few things to be aware of is that when a COOH acid loses a hydrogen, it always loses that final hydrogen. Okay? It's always that last one that is the acidic hydrogen, the one that comes off. Now, when you're writing these dissociation equations, you need to remember to write the states, the charges, and you need to make sure that you have balanced them. Here's just a few examples to make sure that you feel good about everything. First one's really straightforward. NaCl becomes Na plus and Cl minus, both are aqueous. Fe2SO4 3, you have to remember that the SO4 stays together and that your coefficients become 2 and 3. HNO3, you need to remember that the NO3 stays together, and don't forget your charges. And finally, just a reminder once again that if you have a COOH acid, it's that final H that comes off. So there will be a bunch of practice. And then, do you guys remember what dispersion is? Dispersion means that they don't tear the atoms apart and become ions. It just, the molecules separate from one another, okay? You can also call it dispersal. So you are looking for molecular compounds. Those are ones that don't start with a metal or NH4. And also we're going to, they're not going to start with H, because if they're acids, they do dissociate. So when you're writing a dispersal equation, your initial formula and your final formula should be the same. Nothing should change. Okay, the only thing that should change is the state. is good. Okay. And I think that's it. Electrolytes and non-electrolytes, basically, this is just everything we've done before. Substances that conduct electricity in solution. So if you're asked to define an electrolyte, you need to give me a few definitions. You need to tell me it can conduct electricity in solution. And why does it do that? It does it because it contains ions. And I should have put a little something extra in here, not just any old ions, but freely what? Moving ions. So you will then be asked to identify your electrolytes, which are your ionic compounds or your acids. And you'll also be asked to identify your non-electrolytes, which are your molecular non-acid compounds. And that is kind of it there. Okay, so you'll see we have dissolved ions on the left. We have dissolved molecules on the right. Charged particles on the left, no charged particles on the right. And you can see here with our electrolyte, we have the ions and they are moving. Okay, all the positives move in one direction, all the negatives move in the other direction. And what do you notice about the light bulb? It lights up, yes, because we have completed the circuit. If we have a non-electrolyte like sugar, it's got some polar areas on it, but overall it has no charge. Do those particles move other than randomly? No, there's only random movement. And you certainly don't have charges flowing. And so what do you notice about the light bulb? No light. Would we like to see a few samples of substances? See if they light up the light bulb or not? Okay. All right. Are we still plugged in? We are still plugged in. Good. So we agreed water does nothing. That's not very exciting. We have some 1 molar KSCN. That is potassium thiocyanate. SCN minus is a polyatomic ion. Okay, so we're going to try that one out and see what happens. Here we go. Oh, have I turned it on? Nope, it's off. There we go, that should be better. Ooh, yes? Nice and bright. And I'm just going to use my water to rinse that off. Okay, so that was 1 molar KFCN. Now we have some 1 molar HCl. I'm going to give this a couple of check marks because it was bright. Okay. 1 molar HCl. I'll give it 3 check marks. Here we go. Also bright. Is it brighter than before or no? About the same, right? Okay. Let us try some 0.1 molar HCl. What do you guys think? Any predictions? Maybe less bright? Let's take a look and see what happens. Not much difference. Shall we try diluting it another 10 times to 0.01? Okay. And this is just going to be like a ballpark, okay? I'm not getting really, really fancy here. So I'm going to put in about 10 milliliters. There we go. And then I'm going to put in about 90 milliliters. So this is 0.01 molar. We're finally, it's a little bit dimmer now, yeah? Okay. What does that tell you about electrolytes? What do they need? What makes something a better electrolyte? It has more something. Ions. Yeah? So this one, the more dilute sample had fewer ions. The more concentrated sample had more ions. So the more ions you have, the better of an electrolyte you have. Let's just write that down real quick somewhere, anywhere. More ions equals better electrolyte. Okay, so we've done a salt, we have done an acid. Let's try, what else have we got here? We have 0.1 molar NaCl. What do you guys predict for the 0.1 molar NaCl? Bright, dim, none? Probably similar to the 0.1 molar HCl. Let's see if it is. Yeah? Okay. There we go. And let's rinse that off with our water. Where's my water? There's my water. Okay. And now we're going to do some sugar. Where did I put my sugar water? Sugar. Where'd you go? Where did I put the sugar water? Oh, right here. Okay. What do you think? What do you guys think is going to happen with sugar? We have 1 molar. C12H22O11. Not going to light up. Let's see. Where did I put it? Right here. And lo and behold, it does not light up. Woo! Okay. Next, we have, did you want a base or did you want another acid? Yes. Tap water. Vancouver water is very soft water. That means it doesn't have very many dissolved minerals. So it doesn't have hardly any calcium or sodium or anything in it. So it's going to work pretty much like, so when we have deionized water, I fill it with tap water because we're a high school and we don't have a lab aide who works our distiller anymore. So we just pretend it's the best. It's pretty good. So yeah. just tap water. Okay, I'm just going to rinse that off. Here comes a base. Here is some 1 molar KOH. What do you guys think? Tell your partner, what do you think? We ready? Yeah, because it's bases are just ionic compounds, right? They just happen to have their ion be OH. And our last couple of ones, what we're going to do is we're going to do 1 molar CH3COOH. What should happen with that? It should light up. Bright or dim?
Bright.
Bright. Okay, let's see what happens. Oh, well, that's new. Okay, so that's 1 molar acetic acid. Interesting. Let's try 0.1 molar. Okay. Water, water, water. There we go. And 0.1 molar. Oh, very dim. Yes? Have a little chat with your neighbor, see if you can think of why that might be. Yes. It does lose a final hydrogen, but we know that if we have more ions, it will be brighter, yes? It will be better conductive. So over here, we have 1 molar and 1 molar is 2 molar ions, yes? 1 molar and 1 molar is 2 molar of ions. Now we have 1 molar CH3COOH. What is the only possible thing? Oh, and let's just, while we're here, let's do sugar. C12H22O11, 1 molar. It's the same thing, right? So I have 0 ions. Yes? How is it possible for this to happen and get it to be dim? Yeah? That's a good idea, but they're no further apart than they were for HCl, right? Because we've got the same number of particles per liter. Yeah?
In some way, like less.
It is in some way less efficient, but why? What was it about sugar that made it not? Sorry, go ahead. Yeah. What was it about sugar that made it not conduct? It didn't dissociate. So what could it be about acetic acid that makes it not conduct as well? It dissociates less. So what's going to happen is you're going to get only partial dissociation. So if you have like 1,000 particles of CH3COOH, 900 of them are going to stay together, undissociated, and maybe only 100 of them are going to split apart. So acids, because you remember they're molecular, they're not ionic compounds, right? So they're more covalenty than those ionic compounds. So those bonds, depending on the acid, are going to be either more ionic or more covalent. Yeah? So some of them will behave more in an ionic fashion, like HCl, HBr, right? This one dissociates 100%. And that's why we got a bright light. But this one, most of it stays here, and only some dissociates. Okay? And that's why we get a dim light. And in grade 12, we're going to spend a lot of time looking at this kind of reaction. This year, you just only need to know that it like exists. Yes? So we would call this kind of substance, it's not a strong electrolyte, it is a weak electrolyte. And we don't even need to write this down, because if we go to 8.1, is it D? No, E. 8.1E on page 16. So acids, if we have strong acids, that's what we call them. If they dissociate completely or ionize completely, then those are what we call strong acids. So you'll notice that what we've got here is we have one-way arrows. Okay. And we have 1, 2, 3, 4, 5, 6 strong acids. That's not actually that many. Most acids are not considered strong. Most acids do not dissociate completely. Okay? All the other acids ionize or dissociate only partially. Okay, so these are our weak acids. And those are all of our other acids. So ethanoic acid, CH3COOH, is one of them. But we have HF, HCN, H2CO3, HNO2, and a ton more. Okay? You're not responsible for knowing those ones. You will be responsible in our next unit test, not the one coming up next week, but the one after that, for memorizing your strong acids so that you know that they dissociate completely. How are you going to remember that? There's 2 mnemonics. So I brought no clean clothes. So we have so I brought no clean clothes. Yeah? Then the only tricky part is just remembering that it's SO4, ClO4, and NO3. okay, and that there's an H. The only one that has a 2 is the H2SO4, okay? Or, if you don't like that one, you can ask your good friend Chloe Kleiberson. Yes? So we have Chloe Kleiberson. Okay, so either of those can help you to remember them. It's not a big deal if you don't remember them this year. I'd like to have you memorize them just because it'll help put them in your mind, just like having nitrates always soluble and those sorts of things. If you choose not to take the AP chemistry test, you will not need to know them by heart for Chem 12. Okay? And by the way, if you sign up for AP Chem 12, that does not mean that you have to write the exam. Okay? You can choose to take AP Chem and not write the exam, or you can choose to take it and write the exam. Either way is fine. And by the way, in grade 12, all your tests are identical to regular Chem 12. So no more hard tests. Well, I mean, they're hard because Chem 12 is a hard course, but they're not like harder than regular Chem 12. Okay? All right, so what does this look like? Well, if we have CH3COOH, you'll notice that we have this reversible arrow. So what's going to happen is that sometimes these guys are going to reassociate. They're going to come together. But every time that happens, another undissociated one will split apart. Okay, so it remains, the concentration of each species remains constant. Yeah? And that's what we call an equilibrium arrow, and that's what almost all of Chemistry 12 is equilibria, where we have things going back and forth. Okay, so this is just partial dissociation. And what does that look like if we were to take a snapshot? Well, you'll notice we have undissociated acetic acid. Yeah? Only a very, very little bit of it is dissociated. Most of them are together. So you don't get very many ions for a high concentration. Whereas over in HCl, everybody is dissociated. Yes? Okay, so we're going to leave it there for today. You can, for the rest of class, work on 8.1a, 8.1b, 8.1c, and I'm also going to give you the quiz, okay? So over the weekend, your homework is these three, all right? And also the quiz, and then if you want to review anything more for your test next week, you know where to do that, yes? Okay, so on Teams, right, if we go to, where is it? Upcoming quizzes and tests. Oh, see more. Extra practice, regular stoichiometry, limiting and excess, percent yield and percent purity. It's in with the quiz. Okay, so it tells you, Hebden page 127, numbers, suggested numbers 8 and 9. I mean, you can do the whole thing if you want to, but that kind of seems a bit excessive. But if you have no problems with regular stoichiometry, don't worry about that. There's some stuff here for limiting and excess. There's some percent yield and percent purity in there. Okay, so if you do the quiz and you're like, oh, I didn't do so well on this thing, you can go find some extra practice. Okay? Test is on both Unit 7 and Unit 6. And no, you don't have to give specific steps for the titration on the test. Okay? Is good? Yes? 7.4 is not on the quiz, but it will be on the test. Okay, so if you want to work on that over the weekend, you can as well. But I will give you a little bit of time, maybe on Monday, to do some of that. Yeah? Okay, cool. That's it. We're done for the day. But I would recommend you spend the next 15 minutes doing a little bit of 8.1, 8.2, 8.3. They're easy, okay? Just like go slam through a few of them, and then you won't have as much on the weekend. It'll be nice. You won't regret it if you do it now. You will regret it if it's sitting over you. Hi. I think it's still okay. I go through my bag. I bought a bag this morning. I thought it did. But then it was too late. Yes. So I will look at the side. So why is that? That's not much fun. But I'll learn. And with like so I will find out. I will. Oh, so you're like, I don't need to rewrite it. That's smart to me. These are quiz dolls. Was not supposed to be find this. By the way, it was raining about 6 So everything else is right. Wait, oh, no, this one. Yeah. Oh, did you do the demo yet? Yes. Oh yeah. It's okay.
Where's the carriage? Oh, there it is.
I'm gonna low-key just take it on my jet. I have a lot of things.
Okay, so wait, let me write this in my reminders. I'm gonna forget. Okay, so I mean, look at that. Okay, I did it. I would like to go to one that I would like. I was then I think like I was pushing right up these very months and I know I would want them. I don't buy it. What time? Wait, how is FE aqueous? And then it made me.
No, because it is so free.
My friend mom. Wait, so one, and then you have to draw one. Wait. Wait, so for one FE
Right, copper. Okay. Because I'm like, well, you know, so it's like, okay, but it explains. Should be.
No, that is. That was big. So that's solid.
Towards the electrolytes, but other than that, that's what I'm doing. Yeah.
It's mine. What do you have to do?
This one, I think I still have to go to something. Or I can send it to Billy. Like,
Is it still open? I mean, yeah, it still is.
We can go. Wait, I mean.
I thought it was all Friday nights. I thought everybody got Friday nights.
That's my dog.
That's a dog.
That's a dog. You can barely see it.
Wait, do what?
I think I've sold
Squeezing it into the bubble. And then. Hi.
Borrow a stapler for my labs.
Yeah, there's a couple of them right there. Yeah.
Oh my god. And that's
One more HC.
sure?
No, it's the hardest
Sure?
really adverse.
Unless it's no, that's oh yeah, that's all. No, it's not always. It's not, it can be.
No, but like all of these ones.
I don't know. Okay,
Yeah,
so AB plus is an aqueous, right? No. And like CL minus.
If we know what we're doing, yeah, if we know what we're doing, it's fine.
Wait, because I think they're all aqueous now.
Yeah, they are.
Sodium. Let's ask.
But I'm talking about
And then you don't write the H, right? Yeah, you don't write the H. I need periodic table. Never mind, you can have it. What's sulfate? Sulfate. Two.
Four. It's four. It's a four.
No, I meant two after NH4.
Maybe I should get like it.
Wait, Hershey, could you not cross right now? Yeah, but you have to do that, right? Green tea. She's not letting me do a retake. I need SO4. Okay, you could have it.
You know SO4. SO4 is?
No, but like, I forgot the charge.
SO4 is 2 minus. What's the charge of sulfide?
3.
2. Because it's in group 16.
Oh, sulfide.
Sulfide. Sulfide is -2. Sulfate is -2.
There's
Sulfite is also -2.
And that one's sulfide.
That one's sulfide.
Okay. Girl, what are you doing? It says calcium, not potassium. It says calcium.
No, but I was gonna do this one, so
You're doing two at the same time. No, this is CA carbonate.
no, but I still gotta do it later.
Two.
I will do it later.
CO.
There is a later. I'm gonna look at the cross on that one. Is there something wrong with that one?
Like, oh, we gotta pack up. We gotta pack up, Dorothy.
Wait.
I need my periodic table now. Why are you skipping us?
Oh yeah. I didn't even know.
No, we did. You weren't supposed to
I
come.
know.
But like because we suck. And no, Mr. Dudley mentioned during the rehearsal, he was like, guys, since nobody showed up, we have to do it again. And then nobody showed up today, so I was like, what point? You know?
Oh yeah, the quiz.
I started getting grams of each.
Thank you.
And he literally gave me class list to check off.
Don't
people
leave
that,
the practice.
get going. That gave me an email. Oh, this guy.
There we go.
Thank you. This is our quiz that we were supposed to take and did not take.
Okay.
Wait, why is
No, there's an answer key on the back. Answer
Hey,
key
that's
on the back.
we could have just taken it today then. Oh,
But I'm not going to be marking it. So yeah,
never mind.
yeah.
You can work it.
That way you can mark it yourself. Just sit down and pretend it's a quiz.
Yeah.
And then you mark it. You do that. Oh, whatever. Yeah.
Okay. Yes. Say hi to Lucy for me. Okay.
I can also. He's not an OG. Dude, I didn't know. Well, that's very good.
Have a good weekend.
I did. Well, I don't even have an hour.
Have a good weekend. Yes.
Is that, you know the way you lit this up?
Yeah.
Is this how acid power batteries work?
Very similar. This one is the opposite of an acid powered battery, because in the acid powered battery, what you're doing is you're getting voltage out. This one, the voltage is supplied, and that's what lights the light bulb.
Oh, I see.
Yeah.
Because I was thinking, like, why don't we just use acids to power the light bulbs? That already exists.
What's that?
I was thinking, like, why don't we just use acids to power light bulbs? And I realized that already exists.
True.
That was not 1,000 Wait, Edward. I thought it was like a Nixie Edward. Edward, are you no, sure. But please, what was it? I was a silver too. He does 1,000. No, Edward, I need more ocean. Not that ocean. 6. But I gave you my sister and I got 13 silver. Edward, I was in like power line. You know why? Like you don't get rid of it. Not even Howard? No, like way more.
Fuck me. Bye.
Sorry for that.
Oh no, it was fun. I was like worried I wasn't gonna have anybody throw pie at me, so thank you.
See you.
Bye. See ya. Right, October 1st.